Okay, hello and welcome. We're going to do a quick little video about plate tectonics, and we're going to cover several different topics within this. So in a short video, a lot of information. Okay, take a look at what I've got here. I've got a beaker of water. This is just water with food coloring that I've heated up. I've got a tank of water, and then the third thing will be these two blocks of wood. And so what I'm going to do in just a moment is to set this beaker and all inside the water tank, and then we'll put the blocks of wood like this, okay, right on top. All right, so before I do that, just in your brain kind of think what will happen, how will this what this is supposed to be is the core, by the way, mantle and crust. How is the energy from the core going to affect the crust here as we go? Okay, so that's just something to have in mind as you go. Let me stand up here. Set this in, set this here, there we go. Okay, I don't know how well you can see that. I think it's working pretty good. Okay, so the energy from the core is rising up to the mantle. It can't go any further. It has to pull outward like conveyor belt, and that caused these two crustal plates, these pieces of the crust, or this crust, to just kind of move on their own to the side there. Okay. That's exactly what hopefully I thought you would would happen, and it leads to then the discussion of a German scientist named Alfred Wegener from the 1950s. And Alfred Wegener proposed the idea of continental drift. He said that the continents are literally drifting around the world, and he had lots of good evidence for this idea that Africa and South America would fit really nicely. There's a lot of fossil and geological evidence to suggest that as well. Really strong piece of evidence. But despite that, nobody really bought the theory, and they didn't believe it because Alfred Wegener couldn't explain why it does it or how it's able to do that. And if you think about it, an entire continent drifting around the world sounds like not an easy thing to do. Okay, what Alfred Wegener didn't realize was that the Earth, as we just saw here, is broken into about 7 major plates. The crust is broken into about 7 major plates, and this black blob that I drew is supposed to represent a continent. And so if the plates move, the continents go with it. That was the mechanism. The continents are riding like piggyback on top of the crustal plates. So if we actually had what we saw there in our little tank of water, where it breaks like this, the entire continent itself could break in half. Okay, and you might look down below and go, well, what's happening there? If I look into that, will I see all the way down to the core? Well, no, because the melted rock is making its way up. So new ocean or new sea floor is being created. New Earth is being created. We call this motion, as we're moving away from each other, we call this diverging plate boundaries, to diverge, to move away. Okay, and whenever we have diverging plate boundaries, we have a little bit of earthquakes as it's moving, and then we certainly have volcanic activity making its way up, causing that spread. Okay, now the question that maybe comes from that is, well, if new Earth is being created, we call it seafloor spreading. If that's occurring, then the Earth has got to be getting bigger. Somewhere we've got to account for that new Earth, all right? And so we could go to a different place on the Earth, and 2 plates might be coming together. We call it converging boundaries, okay? So 2 plates coming together. How does that allow for more Earth to be created somewhere else? Well, if we crumple that up like this, as they collide, that would give us more room for the diverging boundaries, okay? And India, Asia came together, converging boundary. We have Mount Everest. So the tallest mountains in the world were a result of tectonic activity. Another interaction as the plates come together, converging boundaries, is when they hit, one actually gets pushed down below the other one. We call that subduction. So this plate on this side gets subducted down below this one. And as we know, I hope, the deeper you go into the Earth, the hotter it gets. We get to a point where this crust melts, makes its way up, and then we have a volcano somewhere along the lines just inward from that contact point, okay? So where we have converging boundaries, we have earthquakes as this is being pushed down below, but we also can have volcanic activity that comes with that. Okay, lastly, the third interaction that we have with these plates is not coming together, not moving apart, but simply sliding past each other. We call that a transform boundary, okay? And again, it wouldn't be nice and smooth like this. It would lock into place, pressure builds up, and then one big release as an earthquake. When we have transform boundaries like this, because there's no subduction, nothing from underneath is making its way upward, there's really no volcanic activity associated with this. This is just earthquakes, okay? And maybe the real world scenario of this would be this plate over here would be the North American plate. This is the Pacific plate. Most of the United States, including California, would be on this side. A little bit of California on this side, right? This would be the San Andreas Fault. It's a transform boundary. And so if you have your home in LA and you just live there for a few million years, eventually you'll be up in Alaska because it's sliding northward, okay? So there's an example of our third type of plate interaction. Okay, so what do we have to put it all together? We have a quick little model of the core, mantle, and the crust, how those things move. We are introduced to the idea of continental drift and plate tectonics. And then lastly, we looked at the three different interactions, converging, diverging, and transform boundaries that are a result of the movement of the crust. Okay, hope that works. And if you have questions, let me know.